All right, so today we're going to take a look at a different topic. Okay, nothing to do with solving triangles like law of sines and cosines. We're going to look at what's called the trig form of complex numbers. Basically, what trig form allows you to do is multiply and divide. Those are two of the things very quickly. Okay, I'll go over how we would multiply and divide the old way using like I squared and foiling. This is going to be much better. Okay, once we learn how to do it. So just as a reminder of how you write a complex number in standard form, real part plus or minus imaginary part. So something like that is standard form. Real part plus imaginary part. So what I'm going to do first, before we even get to trig form, is I'm going to show you a couple things you can do in standard form that we haven't done. Okay? One thing we've never done is graph a complex number. Okay? And it's very, very simple. Okay? You have two axes, one for the real and one for the imaginary. And you graph it just like you would the coordinate AB. Like if your real part was A and your imaginary part was B, you graph it just like AB. So what's happening is A is normally which axis? Which axis comes first in an ordered pair? Yeah. It's normally the X. So what's happening now is the real number, the real part, is taking the place of the X. And the second axis is normally your Y. What's happening there is the imaginary part is taking the place of the Y. So, in the complex plane, you have two axes. The real axis takes the place of the X. The imaginary takes the place of the Y. Positive and negative is exactly the same as it always is. So what we'll do is just look at some examples of graphing complex numbers. Okay, and the point of this isn't really just to graph them, but when you have a complex number and you want to write it in trig form, the first step is to know the quadrant it's in. So if you can graph it, then you can figure out the quadrant it's in. That's why I'm showing you how to graph. Okay. So let's start with -4 minus 2i. So from the origin, what directions would I go to graph -4 minus 2i? Chop, chop. So let's label these axes first. Which axis is which in the complex plane? Yeah, so the real axis is horizontal. Okay. And the vertical becomes imaginary. So looking at this number, what's the real part of it? -4. So on the real axis, we're going to -4. So which way would that be? Left. So we go left 4. And then on the imaginary axis, what's the imaginary part of this number? -2. So what direction would negative be on the imaginary axis? Down. So we're going left 4, down 2, and there's our point. And again, the real point of that is so you can figure out the quadrant. It's quadrant 3. Okay, let's try this one. 2 plus 3i. Dylan, can you tell me how to graph that one?
Left 2, up 3.
Yep, left 2, up 3. And what quadrant is that in?
Quadrant 2.
Good, say quadrant 2. 5i. Sam, how would I graph 5i?
It would just be up 5.
Yeah, you could think of it, if you want to think of it as a complex number with a real part, it has a real part of 0. So don't go left and right. Up 5. And then 6, same idea. Think of it as no imaginary part. It's just 6 on the real axis. So it's right there. Those 2 points are special, the last 2, because they're not in a quadrant. They're on an axis. So we'll talk about that. But any questions on how to graph a complex number? Okay, next thing we're going to look at is absolute value. You can find the absolute value of a complex number, and that's going to be something we do next. How can you define absolute value? What's one way to define it? Yeah?
The distance of a point from 0.
So that's a geometric definition of it. It's the distance that a point is from 0 on a number line. Now, in 2 dimensions, we don't really call it 0. What do we call it in 2D? Yeah? Origin. The origin. But the definition, other than that word, is exactly the same. The absolute value of a point is the distance that it is from the origin. So, how do you think you could find, I didn't draw it perfect, but how do you think you could find that distance? Yeah?
You could make it into, well, you can make it into a triangle.
Yep.
And use the lengths.
Yeah, we just use the Pythagorean theorem. And there you go. So just find the hypotenuse using Pythagorean theorem, and that's how you find the absolute value of a complex number. So, if you were graphing a plus bi, the bottom side would be a, that's how far over. The height is b, that's how far up. And the absolute value is the distance from your point to the origin. Sometimes we also think of it as a radius. And we're going to be doing that very soon. You could think of that point as being on a circumference of a circle. And then it's like a radius. So, square A, square B, square each leg, add them up and take the square root, and that's how you find the absolute value of a complex number. Remember, when you plug it in, the I has nothing to do with finding the absolute value. Just that number, that number. Okay, any questions on that? Great, so now we'll take a look at an example. Keep in mind all the rules. If you end up with square roots in the denominator, which that shouldn't happen here because you really don't have fractions, but if you did, you got to fix it. If you get a square root you can reduce, you got to reduce it. So let's find the absolute value of this number. Picture is not necessary, but if it helps you, go for it. Hey, can anyone set up my right-hand side to find the absolute value of 3 plus 4i? Leo?
Square root of 3 squared plus 4 squared.
Yep. 3 squared plus 4 squared. And if you do that out, you get an absolute value of 5. Okay, so that's a 3, 4, 5 right triangle. That one comes out nice. They don't all come out nice, obviously. Okay, any question on how we found the absolute value? Okay, finding that is important because this distance right here, which we're going to think of as r shortly, is one of the 2 things that you need to write a complex number in trig form. Okay, this I'm going to hold off on, and we're going to jump to trig form. So in standard form, you have a real part plus or minus an imaginary part. Now you might be like, well, why did I switch all of a sudden to using x and y when before I was using, I think I used a and b, or yeah, I used a and b. I'm just using x and y because now we're going to get into more looking at this on a plane, and I want you to remember x is horizontal, and I think most people make that connection, and y is the imaginary, which is the vertical. All right, so let me kind of just draw what we have right here. Okay. So what I've got right now is my point x plus iy. I've assumed x and y are both positive. I put it in quadrant 1. It doesn't matter. Okay. If it's not in quadrant 1, I'll show you what you need to do. So if you make a triangle out of it, the bottom side of the triangle has a length of x. The height of the triangle has a length of y. To write this in what we call trig form, you need two things. One, you need the distance of that point to the origin. Okay? And we're going to think of it as a radius. Pretend like that point is on the circumference of a circle. Right? So we're going to think of that as r. And the other thing you need is this, theta. Theta is the angle with the hypotenuse and the positive x-axis. So the two things in red are what you have to get for trig form. So x and y are going to be gone. X and y are standard form. We're going to get rid of them. And the way we're going to get rid of them is we're going to use right triangle trig with two different trig functions. Let's start with x. What trig function could I use that would involve x and r? Yeah?
Cosine.
Yes. You could set up an equation involving cosine. Cosine is adjacent divided by hypotenuse. Now my goal is to get x by itself so I can plug in something and get rid of x. So how would I get x by itself there? Okay?
Just multiply by r.
Multiply by r. Multiply by r. There's your formula for x. R cosine theta. In a minute, that's going to get plugged in right there. Okay, let's do y first. So now, what trig function could I use that would involve y and r? Yep, sine. Okay, so sine is opposite over hypotenuse, y over r, and I'm going to do the same thing to get y by itself. And now I have a formula for y. I'm going to make those two substitutions, and that's going to give me the formula to putting a complex number in trig form. So we'll have gotten rid of the x and the y, and instead we're going to introduce an r and a theta. Okay, so x becomes r cosine theta. The I just stays right where it is, and the y becomes r sine theta. Now there's two factors here, this one and that one. What do both of those factors have in, I'm sorry, there's two terms. R cosine theta is a term, IR sine theta is a term. They each have a factor in common. What factor do they both have in common? R. Some people say, what about theta? Theta is not a factor, theta is an argument. It's something that's plugged into a function. Since they both have an r as a factor, we can pull it out and write it just like that. That is the trig form of a complex number. R, and then in parentheses, cosine theta plus I sine theta. So, if you're wondering what would a final answer look like in trig form, you'd have a value for r, which you need to find. Let's pretend r was 6. And you'd have a value for theta, which you also need to find. Let's pretend it's 15. That is what a final answer would look like if you write a complex number in trig form. You don't do anything with that. If you said, well, what if I took the cosine of 15 and multiplied by 6, and then took the sine of 15 and multiplied by 6, you would be changing it back to standard form. So if you stop here, you have it in trig form. If you do this out, then you're changing it back again, which usually we don't want to do. Sometimes changing it back is a good way to check your answer, but when they ask for something in trig form, you stop there. Okay, so the two things, I already tried to explain to you what they are. you need to find r and theta. R is the distance from the origin in this picture. That's r. It's basically the absolute value. And theta is the angle between the positive x-axis and the hypotenuse. And that's what I tried to show you right there. Angle between the positive x-axis and the hypotenuse. Okay, so now we just need to discuss how to find those two things. Okay, and I'm going to guess most people probably already know, using a right triangle, how to get the hypotenuse. We've already kind of done that. And also how to get theta.
Can you just show the example answer just for another second?
Yep. These can be messy. Sometimes the radius is a square root, because we'll talk about how you have to find it in a second. The formula involves a square root. Sometimes theta can be a decimal. But a lot of times the answers don't come out nice like that. All right, so looking at the diagram, how would you find r if you knew x and y? Yeah? Right, you're going to use the Pythagorean theorem. That's why I said r is a square root a lot of times, and you get a decimal. Now, how would you find theta if you knew x and y? What trig function would you use? You'd start by setting it up with tangent, because it involves opposite and adjacent, but then you'd have to get rid of tangent using inverse tangent. So that's the whole key. So inverse tangent is going to help you to get this angle. Pythagorean theorem will help you to get r, because you have to figure out those two things for each problem. So I'm not going to draw it out. I just explained it in words. I'll just show you the formula. Well, you know the formula. Okay, so to find r, use the Pythagorean theorem. And now this is where graphing it is important, because now, depending on your quadrant, that's going to change how you find theta. If you're in quadrants 1 or 4, all you have to do, if you look back at your picture, is inverse tangent of y over x, just a right triangle trig problem. But one of the characteristics of inverse tangent is when you type in y and x and then inverse tangent, hit enter, your calculator will always give you an answer between -90 to +90. Your calculator will never give you an answer outside of those two numbers I just wrote. So, what that means, you're always going to get an answer in either quadrant 1 or 4. But that's a problem, because what if I graph a point and it ends up over here? What if it ends up in quadrant 2, like we did one somewhere? Right here, like -2 plus 3i. That's in quadrant 2. So how would you find that angle in quadrant 2? You can't just use inverse tangent y over x. It's not going to give you an answer in the second quadrant. But what you can do is just add something to it. All you have to do is add pi. And what that does is pi is 180 degrees. And it shifts you over from quadrants 1 and 4 over to 2 and 3. So if you're in quadrants 2 or 3, you have to add something to the inverse tangent. Pi if you're in radians, 180 if you're in degrees. Right. So now you know how to find r using Pythagorean theorem. You know how to find theta if you're in a quadrant. But where else can you be besides in a quadrant? Yeah?
On an axis.
On an axis. How can you quickly tell if a coordinate is on an axis? Coordinates on an axis all have something in common. Leo?
One of the variables is 0.
Right, one of the parts of the coordinate is a 0. Well, let's pretend I gave you this. and I wanted you to plug this coordinate into a formula. First of all, you wouldn't, because 0, 3 is it's on an axis. It's not in a quadrant. But for some reason, let's say you thought that was in quadrant 1. What would happen when you plug in 0, 3 into this formula? Yeah.
You get a no solution.
Yeah, you'd end up dividing by 0. Okay? So these formulas don't work for points on an axis. They only work for exactly where I showed you they work, quadrants. So what do you do if it's on an axis? You just have to memorize the answer. It's 4 numbers: 0, 90, 180, 270. 0, 90, 180, 270. So you have to just memorize those 4. Now we've covered all the different places you could have a point and you'd have to find an angle. On an axis, in a quadrant. Pythagorean theorem, it works everywhere. Pythagorean theorem works in a quadrant, it works on an axis. But if your point is on an axis, you really don't need Pythagorean theorem. Like if you graph the point 0, 3, you should be able to figure out the distance to the origin without Pythagorean theorem there. The only time you really need Pythagorean theorem is when your point is at an angle. And then you have to find a hypotenuse. Okay, not when it's on an axis. Okay, so let's practice writing that number in trig form. Okay, that's standard form. Real part plus or minus imaginary part. Can someone remind me the 2 things that I need to write this in trig form? I need to find, yep.
R and theta.
I need to find R, and I need to find theta. It doesn't matter which one you start with. So, Caleb, which one do you want to start with? R. Okay. So if you want to graph it, well, I'll graph it first. It's left 2, up 2. So can you set up my formula for me, Caleb, to find the radius from here to here?
2 squared plus 2 squared and the square root.
So 2 squared plus 2 squared, take the square root of it, and that's your radius. And Megan, what do you get when you do that?
2 squared is 2.
Yep, you get the square root of 8. As always, we reduce it. Square root of 4 times square root of 2. So we can write 2 root 2. Okay, now my angle. Okay, angle depends on the quadrant. If we're in 1 and 4, we use the top one. 2 and 3, the bottom one. Okay, doing that, what quadrant am I in here?
You're in the second.
I'm in the second one. What is the formula to find the angle in the second quadrant?
It's pi plus inverse tangent. And then over x, which would be
And I should be a little more accurate with this. I mean, you can make it negative. So,
it'd be 2 over negative 2.
so y is 2, x is negative 2. When you divide them, we could just do the inverse tangent of negative 1. Okay, so let's see what we get. So pi plus inverse tangent, negative 1. Now, since she said pi, that's why I kept my calculator in radians. If she had said 180 plus, I could have done it that way and changed the degrees. Okay, so we get 2.36. Okay, now we have to write the final answer in this form. Exactly what's in that box. Just fill in 2.36 and 2 root 2 and then stop. Okay, let's write it out. So R, parentheses, because it's distributed, cosine theta, plus I sine theta. Now, do you do anything with that? Do you have to do anything, Megan? No, you stop there. If you started to do this out, let me show you what happens. I already told you, but I'll show you. I'm going to take 2 root 2 and I'm going to distribute it to the cosine of 2.36. 2 square root of 2 times the cosine of 2.36. I got negative 2.0, we'll just call it negative 2, okay? Because my decimal is a little off. Negative 2. That's what I started with, negative 2. Right. If you do the same thing again, distribute the 2 root 2 to the sine, you would get 1.99, 2, basically 2. So you would have a 2 times an I. 2 times I. So if you do that out, you're changing it back. Okay? Any questions on that? Okay. So the rest of 8.3 and 8.4 is just working with numbers that are in trig form. Okay? To do 4 things. Multiply, divide, super easy. Raise to a power, very easy. Take a root. There's a process for it. Never changes, same process every time, but it's kind of difficult the first time through. It's different. All right, so I just said that trig form gives us a super fast way to multiply and divide. I am going to show you the old way of dividing, and I might put one of these on the test, because you should remember how to divide complex numbers in standard form. And I'll give you a hint. You have to multiply by something. Does anyone remember what you have to multiply by? Yep.
Wait, no, minus root.
Yep.
Yeah, what it's called, but it would be 5 minus I.
It's 5 minus I. And does anyone remember what that's called? Yep.
Conjugate.
The conjugate. So if you want to do this out, and this one's not even as bad because look at the number in the top, it's just a 3. So it's just a single distributive property. If this was like a 3 plus 2i, in fact, maybe I could do it that way, but then you'd have a double distributive property. Okay, I'll just leave it the way it was. So you get 15 minus 3i. And then in the bottom, we still have to do a FOIL, so we still get to practice that. So we got 5 times 5. We've got 5 times negative I. 5 times positive I. And then we have a positive times a negative, which is a negative. I times I is I squared. So in the top, not really much we can do with that. In the bottom, negative 5i plus 5i. And what about I squared? What is that? Yep. It's negative 1. So what I really have here is minus 1. So 25 minus 1 gives me, Jay?
Plus 1. Or 26.
26. And now the last step is when you write it in standard form, you need real part. 1526 minus imaginary 326, and you put your I. Okay, not that bad, but there's a better way. Okay. There's a way where we can make all this go away. Having to FOIL, combine like terms, change I squareds to negative 1, combine like terms again, and then separate it into 2 parts. Okay. So any questions on how to do it the old way? Okay, now the new way. The new way is going to rely on trig form. So I have 2 complex numbers here. In a real problem, you would be given a value for R1 and R2, like 5 and 2 root 2. Actually, this bottom one is the one we just did, 2 root 2 and 2.36. It's the same problem. The top one is a different one. And you'd be given a value for theta 1 and theta 2. I'm going to give you 0.93 and the one we just did, 2.36. Now, the reason for what I'm about to show you, it's pretty straightforward, but again, because we've already missed a couple days this week, going over proofs is not my focus right now. Normally I would. It'd probably take about 2 minutes to go through it. Okay, so to multiply two complex numbers, if you put them in trig form, all you have to do is take R1 and R2, multiply them together. The next thing you have to do is take theta 1 and theta 2 and add them up. Excuse me 1 second. Okay, so those are the two calculations. Multiply the radii, add the angles. That takes the place of having to do all that foiling. Now this is multiplying, so there's no conjugates involved with multiplying in standard form, but you do usually have to FOIL, change I squareds to -1s, and then combine like terms. All that goes away with this formula. Okay. How would you prove that this is the formula? Well, you basically put those two things next to each other and FOIL them out. And what ends up happening is you get two trig identities. You get a cosine sum identity, and you end up with a sine sum. We did those back in section 7.5. That's like a cosine, cosine, sine, sine. People kind of remember that pattern? Or the other pattern is cosine, sine, cosine, sine. That's what ends up happening here when you FOIL all this out. Now, based on that pattern, what do you think Z1 divided by Z2 would be? So the top one is for multiplying. This is going to be for dividing. Okay?
Do you want me to say the
Sure.
calculation?
Yeah.
So would it be R1 over R2?
Yep. So first calculation is you're going to divide the radii. And second, go ahead.
And then if you have cosine theta 1 minus theta 2?
Yep. So the second calculation is to subtract the angles. And of course, R2 can't equal 0, because if it did, you'd be dividing by 0. So this calculation is going to take the place, this one right here, is replacing everything that I just did right here. All that is going to go away as long as you use trig form. If your numbers are already in trig form, super fast. If you have to convert your numbers into trig form, I think it would take longer to change everything to trig form and then use this. Okay. In the problem I'm going to give you, they're already in trig form. We already did this one. That was the first one that we converted. So I'm just using our result. And the other one I converted for you. Okay. So they're already in trig form. We're going to multiply them, and we're going to divide them. Okay. Let's start with the product. Okay. To find Z1 and Z2, what do I do with R1 and R2? What do I do with my two radii? Yeah?
You multiply them.
We multiply them. So I have 5 times 2 root 2. What's 5 times 2 root 2? Go, Abby?
It would be 10 root 2.
10 root 2. So there's half the problem. That's your radius. And now I'm going to have cosine of an angle plus I sine. I'm going to fill in the same angle. So Sam, when I'm multiplying two complex numbers in trig form, what do I do with the angles?
You add them.
We add them. So 0.93 plus 2.36, and we're done. That's it. That's the whole problem. Multiplying, dividing, and raising to a power, which I haven't shown you yet, are about this difficulty. Roots are a little harder. Okay, so now let's divide. So now Z1 divided by Z2. We have to take R1 and divide it by R2. But when I do that, what's going to happen that I don't like to have happen? Something we're going to have to fix. Yeah, Sean?
There's going to be a square root.
Right, and we do R1 over R2, which I'm going to do off to the side. I'm not going to do it in the final answer spot yet. I get 5 divided by 2 root 2. which I then need to fix. And I get 5 root 2 over 4. Okay, so that's my radius. I'm just going to move that. Try to move that down. Bless you. Okay, so we've got our radius. How about my angle? What do I do with my angles in trig form when I divide? Okay, subtract them. Now, something's going to happen here. 0.93 minus 2.36. If the directions don't say anything, then it's perfectly fine to leave that as a negative number. So now when we subtract them, we get negative 1.43. If the directions don't say anything, negatives are okay. I'm going to show you a couple ways you can get rid of the negative if you need to. So cosine negative 1.43, I sine negative 1.43. Now, when you get rid of the negative, the radius doesn't change. There's nothing you can do with that unless you want to make the radius a decimal. But what can you add to an angle to make it positive? And it doesn't change the angle, it just adds something to make it positive. Leo?
Add 360 degrees.
Add 360 degrees, or if we're in radians, what would you add?
2 pi.
Add 2 pi. So I'm just going to add 6.28. And that's one perfectly acceptable way to get rid of that negative. 4.85. If you're wondering why I don't have parentheses around the argument anymore, it's because when you have a negative, sometimes it looks like it's a subtraction sign, and I'm trying to avoid that confusion. Now I don't have a negative anymore. Okay, and the third way. I want you to look at, I'm just going to pick two values, cosine of 0.8 and the cosine of negative 0.8. What's the difference between those two results? That's it. Don't think too hard. Literally just, what's the difference between these two numbers on the screen? Yeah, Sam.
Oh, sorry. Nothing.
Nothing, they're the same. Okay. So, when you take the cosine of something, it actually doesn't matter if you have a negative. Okay, that's a rule, that's an identity. You can just get rid of it. So, when I had that negative, if I wanted, I could have just put this. Just leave it off. Now, let's try that with sine. Let's take the sine of 0.7. You can use any number. I'm just using 0.7. Let's take the sine of negative 0.7. Are those numbers the same? No. But what you can do is this. You can take the negative and put it in front. So the sine of negative 0.7 and the negative sine of 0.7 are the same. All I did was take the negative and put it in front. So you could do that here. Instead of plus I sine negative 1.43, you could make it minus I sine 1.43. And the point there is just to get rid of the negative in the argument. All of these answers are acceptable. You just have to look if the directions are specific about having negatives or not. Okay. Any questions on multiplying or dividing numbers in trig form?
Can you show again how you got the radius?
The radius?
Yeah.
For z1 over z2?
Yeah.
So we took 5 divided by 2 root 2. So 5 divided by 2 root 2. And then I multiplied top and bottom by root 2. So at the top, you get 5 root 2. In the bottom, you get root 2 times root 2, which is 2, times another 2 in front. And that's how I got the 4. Any questions on that one? So that's another one that's a little longer because now you have to change this and that to trig form yourself. We've already practiced changing to trig form. All right, so what I'm going to do is I'm going to take a few questions off that because we're going to look at part of 8.4 with the 30 minutes we have left. So let's do 1. You can skip 2. Right, 8 and 10 are good. Let's do 11. Let's just do 11 and 13. So let's change that. And 17. Let's do 17 to 19. And 33. 34. Let's just do 34. And 37. That should be okay. 47. Don't worry about that. It took off like 5 or 6 problems. So that's 8.3. All right, so the last thing that we look at with numbers in trig form is 2 other things, and that's we did multiplying and dividing. Now we look at raising to a power and taking a root. Okay. Raising to a power. Really straightforward. Taking a root, a little more work. All right, let's do this out. Okay, we're going to take and raise this number to the 2nd power and see what happens. Okay, I think you'll notice a pattern when we write this down. In this pattern that I'm about to show you, this is going to take the place of doing a proof. It's not a proof. It's just a pattern that suggests what would happen, okay, but it's not a proof. Okay, so I'm going to square that. So that just means to write the same thing twice. I'm just going to write it out so I can see it. Now, using the commutative property, if I want, I could just take this r and move it in front. If you don't want to move it in that step, you don't have to. But I'm doing that so you can see something. What's r times r? R squared. And now the rest of it is FOIL. So let's do it. What's cosine times cosine? Cosine squared. We have cosine times I sine, cosine times I sine. So how many cosine I sines do I have? Okay, 2 of them. So we have 2 of the cosine I sine. And if you're like, why did he put it in that order? You'll see why in a second. In fact, I'm even going to put the 2 right there. So I have I times 2 cosine sine. As long as you get it all in there, the order you put it in doesn't really matter. Just to make that clear, that's an I. Kind of looks like a 12. All right, so we have 2 of those. And then we have a positive times a positive is a positive. What's I times I? Yeah, I squared. And then sine times sine, Leo?
Sine squared.
Sine squared. Okay, so now that I've FOILed that out, I'm going to put some things next to each other, and I think you'll you'll notice something. Let's look at I squared first. What is I squared again? Yeah. It's -1, so it's really -1 times sine squared. So I'm just going to make that a negative sine squared. Now I'm going to reorder some things. I'm going to put r squared, and I'm going to write cosine squared minus sine squared. That's a trig identity. Okay? And it's a double angle identity. If you're thinking sine squared plus cosine squared equals 1, that's an identity, but that's not this one. Cosine squared minus sine squared is something. And 2 cosine sine is also something. Okay. If you don't remember, on page 415, it says cosine squared minus sine squared is cosine 2 theta. It's a double angle identity. Plus 2 sine cosine. Does anyone remember what that one is? 2 sine cosine? Anyone have a guess what it might be? Based on, it's kind of similar to what we just wrote for the first identity. Yep.
Sine 2 theta.
It is. That's sine 2 theta. And again, that's on page 415. And that's the answer that you get when you square our original number. So based on that pattern, I'm not going to go through all the algebra. Does anyone have a guess if you were to cube it, what the answer would be? Yeah.
It would be cosine 3 theta plus I sine 2 theta.
That would be part of it. Yep.
Times r cubed.
Times r cubed. So, what I'm trying to show you here is this suggests a pattern. And the pattern is, if you want to raise a complex number to a power, you raise the radius to the power, and you multiply the angle times the power. And there's a name for that, and that's pronounced DeMoivre's Theorem. So if you have a complex number in trig form, and you want to raise it to a power, take the radius, raise it to the power, take the angle, multiply it by the power. Now this one is a huge time saver. Okay, I'm going to show you something the old way. You don't have to write it down. I just want you to watch all the steps I have to go through to do it. And then I'll show you a problem the new way. Let's say I wanted to take 2 plus 3i. Actually, let's just do 2 plus 4i and cube it. Okay, the old way. Okay, I would have to write it out. 2 plus 4i, 2 plus 4i, 2 plus 4i, and now I need to FOIL everything twice. So I get 4, 8i, 8i, I get 16i squared. I haven't even done anything with the last one yet. Okay, I'm still working on the first one. So now I have minus 16. So 4 minus 16 gives me a negative 12 plus 16i. Now I'm ready to FOIL it again. Negative 12 times 2. Negative 12 times 4i. 2 times 16i. And then 16 times 4 is 64i squared. And then I would have to keep going. I would change the I squared to -1, combine like terms, and get the answer. Not bad. I could have probably finished that up in another 15, 20 seconds. But let's say you asked me to do 2 plus 4i to the 35th power. So now I'm having to write that out 35 times and FOIL it. There's hundreds of steps and combining. You're probably going to make a mistake somewhere. Well, using DeMoivre's theorem, if you ask me to do this problem, or that problem, I can do them all in the same amount of time. It doesn't make a difference how high the exponent gets. The only thing you have to do is make it trig form first. But it's going to take me probably 60 seconds to change that to trig form, and then maybe another 20 seconds to use DeMoivre's theorem. If you asked me to do that writing out this 3,581 times, I would never finish in the rest of my life. So DeMoivre's theorem will save us a ton of time, especially for bigger exponents. For smaller exponents, depends. Okay, so this is one where, is it going to take more time to change to trig form and then use DeMoivre's theorem, or should we just cube it out because it's only to the third power? Probably could go either way on it, but I want to practice DeMoivre's theorem. Okay, so first thing, we got to get it in trig form. Can someone remind me again, what are the two things you need to change a standard form to trig form? Yep. R and theta. Okay, let's start with R. So I'm right 1, and then I'm up square root of 3 is about 1.7. Sketch doesn't have to be super accurate. Just to get an idea of what we're doing. Okay, so if I solve that with Pythagorean theorem, what would my radius come out to? It would be 2. 1 squared is 1. Square root of 3 squared is 3. 1 plus 3 is 4. Square root of 4 is 2. And now I need theta. I'm in quadrant 1. So what's my formula to find theta in the first quadrant? We haven't done one in the first quadrant. We did one in the second.
Is it inverse tangent and pi?
Yep. You don't add the pi or the 180. Let's do this in degrees since we haven't done one in degrees yet. So inverse tangent. Y, x doesn't really make a huge difference here. You're just dividing by 1. So second, inverse tangent. And I am going to change to degrees. Also, because if you do it in degrees, you're going to see it's actually a nice answer. In radians, you might not recognize the decimal that represents 60. But that's what it is. It's a 60-degree angle. Okay, so I just want to scroll down. Scroll down more. So now write your answer. R cosine theta plus I sine theta. And now I can raise that to whatever power you want, as high as you want. It'll take me no more or less time. What's the power that I had in the problem? Cubed. Okay. So what's going to be my radius when I cube this number that's in trig form? Yep. 8. Cosine. What's going to be my angle? 180. Plus I sine 180. Now, they started out the problem in standard form. What if they asked you to write your final answer in standard form? What would you have to do with this last step?
Distribute.
Yeah, you just distribute it out. So it's just kind of time consuming, but I can show you. 8 cosine 180 is actually negative 8 plus I times 8 sine 180. 0. So if you wanted to get this in standard form, it's negative 8 plus 0 I. Or if you wanted to leave it in trig form, you stop right there. Okay, so can someone just tell me, what did I do to my original number? to get the final answer. What operation did I do here? Yeah.
Raise it to the third power.
We raised it to the third power. What's the opposite of what you just said?
Cube rooting.
Cube rooting. So if you took the cube root of what I just circled, what would you get? Yeah.
The 2 cosine 60 plus I sine 60.
Well, remember, these two things are the same thing. What I had circled here, whoops, and what I had circled right here, they're the same thing. So these are equal to each other. Just like saying 12 feet equals, or 12 inches equals 1 foot. Just two ways of saying the same thing. But if you took one of these and did the cube root of it, you would get something. Yeah?
Would you just get the original problem?
Get the original problem back. So the cube root of either one of these things that I have circled is 1 plus root 3i. And that's what I just said to you. So roots are going to be the last thing we take a look at. One thing to know about roots is you always get multiple answers. How many answers do you get? Depends on the root you take. If you take a square root, you get 2. Cube root, you get 3. So that's why I put here 1. 1 plus root 3i is only one of the cube roots of negative 8. Another one is easy, negative 2. That's also a cube root of negative 8. And the conjugate. Okay, so you always get as many answers as the root you're taking. So tomorrow we'll finish up with finding roots. And that's the last thing in 8.4. And then we'll take a look at 8.5. On 458. 255 is okay. Alright, so just do what I have a box around. If you want to copy the rest, actually, you know what? Don't even copy the rest. This is going to be the last homework assignment for this week. Okay, tomorrow night, we're going to do a take-home. I'll put that on the board. I'll put all the dates when it's due and all that stuff. But there will be no homework tomorrow night from the book. It will be a take-home. So I'm still going to give you the packet, because the packet that I'm going to give you, you need for the next 2 lessons. But you're not going to have any homework out of that packet tomorrow night. You're going to have a take-home instead. Yes? The last slide? Yep.
No, the one we just did.
The one we just did?